And welcome to this talk about Kubernetes patterns. My name is Roland Huß. I'm a software engineer from Red Hat, and currently I'm working on Knative, which is a serverless platform on top of Kubernetes. All the patterns I'm going to show you today are described in this book that I have written together with my friend Biljan. You can get a free copy of this book by following this link. This copy has been sponsored by Red Hat, so feel free to download it. It's a PDF file. You find all the patterns I'm showing you today and many more. Also, you find all the examples which you can try out just to illustrate how these patterns are working. Okay, so let's get started. First of all, let's talk a little bit about what patterns are. Patterns are really a very old concept. They are older than 40 years and come from this original book by Christopher Alexander, written in 1979. In this book, Christopher Alexander and his co-workers are describing a pattern language which can be applied on the field of architecture. So, what is a pattern in that sense? So the classical pattern always has a name. A name is very important because patterns form a kind of a language which is interconnected. So you have patterns which are related to other patterns, and they form a repeatable solution to a certain set of problems. So it's not a very concrete solution, but kind of a solution pattern which you can apply in certain contexts. Here's an example of a pattern which is called city country fingers, and it describes how you should plan for a city so that the people in the city don't have to walk a lot until they reach some green. Of course, this idea has then been slept a while, but in 1994 the Gang of Four picked up that idea and transformed it on the field of software engineering. So this is a very famous book. I guess everybody of you already heard about it. It's design patterns for object-oriented software, and it contains all this famous pattern that we all know and love, like a singleton, like a factory, like a delegate, and many more. Again, this pattern has a certain schema. They are described. They all have a name, and they form an interconnected kind of mini language. Okay, Kubernetes, the other part of this presentation, of course, Kubernetes patterns. But I don't talk much about Kubernetes here because I assume you already know quite a bit of Kubernetes, otherwise you wouldn't join the KubeCon. But just for a very super brief recap, so the main ingredient for Kubernetes is the pod. It's the atom of Kubernetes, and the pod is kind of an abstraction over containers, and they are really describe the runtime contract for a container. So how containers can run within a pod. Sometimes you only have one container in a pod, but often you also have more of them. We will see a pattern which really use this concept in depth. These containers can share certain data via network or via disk. Then your code lives in such a pod and is executed in the pod. And around that, you have tons of other entities which allows you to declare how the application is supposed to be running. And you see here a whole bunch of them. And this is important that you always declare what you want to have. You do not tell Kubernetes do that and that and that step by step, but you declare a kind of a target state. We come to this concept in a little bit later. So now let's dive into the patterns. So we have different pattern categories. So we organized the 24 patterns in different categories. One of them are the foundational patterns. These are more or less the intrinsic features of Kubernetes. The reason for that is that Kubernetes itself, as a platform, is the implementation of certain patterns for distributed computing. And we really find some core concept in the foundational category. On top of that, we have structural patterns, which really take kind of the foundational primitives and combine them into something new. On top of that, or a little bit, not really on top of that, but a little bit on the side are the configurational patterns, which is all about how you can configure your applications. So there are different techniques for that. We have the behavioral patterns, which is really describes the kind of application you're running. So whether it's kind of a stateful service or a stateless application, whether it's running whether it's a batch job or something like that. So this is all combined in the behavioral category. And finally, we have some kind of advanced patterns which do not really fit in the other categories, but they have some more advanced concepts based on all of the other patterns. I have an example for every of these categories. So let's start. First with the foundational patterns. So here we have, as I mentioned, core functionality of Kubernetes like health probes, which are readiness and liveness checks. Predictable demands is about how you declare your dependencies, like resource limits. Managed lifecycle is how you can hook into the lifecycle events for your pod, so that you get notified when it starts or when it stops, and so on. But here we are looking at the declarative deployment. Declarative deployment is all about, so the problem statement is here, and the question is how to perform application installations and also upgrades by configuration only, by declaring your strategy. So we have a core entity in Kubernetes which is called the deployment, and this is really all about declarative or the imperative deployments. Before the deployment entity resource was introduced into Kubernetes, all you could do was kind of a imperative deployment with a client application, so kube control, which allows you to do certain things like rolling updates. So in the imperative deployment, you really say step by step what should be done for a rolling update, which means that you have a set of new copies of your, a set of old copies of your application, a set of new copies, and how you can really scale the old ones down and scale up the new ones. And this is done step by step, as mentioned. However, with deployment, there has been introduced a declarative way how you can declare your deployment strategy by just saying, okay, I want to have a rolling update. I want to have, this is my new image, and now you please do this for me. Deployment Kubernetes resource holds the template for pods so that a deployment can create new pods for you. It creates replica sets on the fly, so it's kind of a manager for your replica sets. So we will see this in a second. It allows also for rollbacks to an older version if you do an update. And several update strategies are declared within your deployment descriptor. Here we see now the different types of declarative deployment. So one is the rolling deployment, which is just about how you can create a zero downtime upgrade. So in this example, you have a version 1.0, which is your old versions. You have 3 copies running in a replica set there, which is managed by a deployment. Then you change the image reference within your deployment so that the target state, which is now the new, which is the change deployment, differs from the current state, which has still the reference to the old version. And then your deployment controller will then create a new replica set with this new reference. Let's say it's version 1.1, and then scales down the old replica set, so from 3 to 2, and scales up the new one from 0 to 1, and then continues until everything is until you have 3 copies of your new application's version and 0 of the old one. In front of your pods, you still have a service, and the selector of the service should point really to both versions, so that you always have the same, so that a user which goes over the service hits either version 1.0 or 1.1, so that there's no downtime for your application. Of course, this kind of deployment does not always work, so your application really needs to be tailored for being able to being upgraded within a rolling deployment. For example, your backend state, like a database, need to be able to run with both versions, so with version 1.0 and 1.1. So if you have a schema upgrade between those versions, you have to do this very carefully so that your database schema really can support both versions. The next one would be a fixed deployment. This is a little bit easier so it's a bit easier from a implementation side. It's because all your old versions are scaled down to 0 immediately at once. And as soon as they're down, then your new ones get been scaled up. So you have a kind of a little bit of a time gap between those versions, so a downtime. And the service actually really is switched over to the new one after that. Then there are variation of both of those deployments. So these 2 deployments, like fixed deployment and a rolling update deployment, are really supported directly by Kubernetes via the deployment resource. But if you want to have some more sophisticated deployment strategies, then you can do that as well, but then you have to do it manually by managing multiple deployments, or you use a platform like Knative, which also supports, which is kind of has a concept of a service, Knative service, which is a simplification of a deployment and which also allows you to create these strategies I'm going to show you now via so-called traffic splitting. So for a blue-green release, you still have your old version 1.0 covered by one deployment. You create a new deployment with a new reference to the 1.1, and so you have both versions running at the same time. However, the service always still points only to the old version. Then you have time to test your new versions, and if you are fine with that, you can just switch up with one call the service over to the new version. In this sense, so in this sense, you also have kind of a zero downtime, but you have an atomic switch also for the service. Another variation of the rolling update is the Canary Release, where you say you make a rolling update, but you stop in the middle. So in this case, you just maybe have 3 replicas for your old in your old version, but then you scale up one pod with your new version, and your service still goes to both of them, but you have maybe 90% of your traffic then goes to the old version, but only 10% to the new one. So you can try out some stuff and say, okay, it's okay for me. Then you can scale up the new version, make it a full rolling deployment, or you say, no, that's not what I wanted to have. Let's go back to the old version. This is easily done. Again, using Knative, this is super simple to do. If you don't use Knative, you can do this manually as well. So here's a nice diagram also from the book where you see how these deployments are working over time. So on the x-axis you have the time, on the y-axis you have the number of instances running. The blue one is the old version, the green dotted curve is the new version. For rolling deployment you have a gradual decrease of the old version and increase of the new version. Fixed deployment you have a kind of a little gap where nothing is running. Blue-green release is you have a certain time where both versions are running, and this is also important to note that for this case you need twice of the capacity for your application, which means your cluster must be large enough that your application can run in 2 copies, which can be an issue or maybe not. For Canary Release, it's a kind of a rolling update which should just stop in the middle like that, and then at the end you can decide what you want to do. Okay, this is all about the declarative deployment. Let's move on to the structural patterns. For structural patterns, structural patterns actually are something about how you can compose your application and can use the primitives of Kubernetes to create different kinds of application. We will look in the most famous one, which is the Sidecar. And the Sidecar container really is about how you can add functionality to an application without actually changing the application itself. This is all about runtime collaboration of containers. We have already seen in one of the slides at the beginning that in a pod you can have multiple containers, and these containers can communicate with each other either via the network, so via localhost and on a certain port, or if set up probably with a shared volume, so that one container can write on this volume and the other one can read it, for example. It's a little bit similar to AOP in the programming world, where you have also this aspect-oriented programming and add orthogonal concerns to your application, like logging or security. And as I mentioned, it's all about separation of concerns. So you can compose your stuff and all the in this example for here, you see that the main container is an HTTP server which serves certain data from a disk, and all the requests that come in just serve the disk. So the main container just is a kind of a static HTTP server. But then you can add a Sidecar container which periodically polls some external storage like a Git repository. And if there's any change, updates the local data so that the next request that comes in for the HTTP server gets the updated data. So with this setup, you do not have to touch the HTTP server at all and can add a new functionality like updating when something changes directly by adding a Sidecar container. And this is a good example how you can really enhance your application without really touching it. And one of the most prominent examples in this category are really service meshes, which actually does this. So inject some certain Sidecar containers into your main application and then add new functionality like tracing and other things, circuit breaking and so on, without actually really any change to your main container. Let's have a quick look into two variations, variations of the Sidecar container. So first of all, the adapter. This is all about how you can decouple the access to a container from the outside world, which means that you can add adapters depending on the needs requirements for certain systems. Here in this example, we have again our main container application. Let's assume you have certain metrics which you want to monitor. These metrics are written down into a file system in kind of a proprietary format. But you have a system like Prometheus which wants to query these metrics. And for this, you just add kind of an adapter which on the one side reads the metrics, and on the other side exposes these metrics to Prometheus in the Prometheus specific format. And so the main application doesn't know anything about Prometheus, but you can still connect to Prometheus for monitoring. And if you change your monitoring system, like let's say you switch to Nagios, then you just exchange the adapter and still your application does not need anything to know about this. This is about how you expose data in a uniform fashion to the outside. And the ambassador is kind of the opposite. It's just how to decouple the container access to the outside world. So it describes how your container accesses the outside world from inside. An example could be a cache which you have locally either, or you want to have a distributed cache. And depending on your needs, you just offer kind of a unique API on localhost, but exchange the Sidecar container depending on the context. So here you have in the upper picture, you have a memcached, which is running locally. Your main application just communicates over localhost over a certain port and does not really know what's happening behind this port. Next, now let's jump to the next category, which is about configuration. And we have already very good direct support for configuration within Kubernetes for application developers. You can use config maps and secrets, but also environment variables to configure your applications. Sometimes you need a little bit more if you have a complex scenario, and I want to show you now in this example how a configuration template works. This is also a pattern, and it's about how you can manage large and complex similar configuration data. Similar in the sense that you might have deployment scenarios where you have different stages, like a development environment, like a staging environment, like a production environment. And all of this has kind of similar configuration, except for certain connection parameters, for example, like a database. So you have the development environment needs to connect to the development database, the production environment to the production database. And of course, you can copy over all this into your applications, but if you do it naively, you have to create different images, container images for all of these applications, which is not very, very nice. But this pattern actually tries to solve this problem by introducing an init container. Init container is something which starts before your main container starts. And let's assume this init container contains a template processor. You have in your image, you have a configuration template, which means all the shared parts are given there, but you have placeholder for the variables, like the database connection URL. And this template processor then would pick up all these configuration parameters from a ConfigMap, for example, and then puts it into the template processor. The template processor also picks up the template, and then the final configuration is stored in a shared volume. And what the main container just does, it picks up this already processed configuration data and serves it and use it for itself. For here, a good example could be JBoss or Wildfly, which is a Java EE application server. And here you see it's graphically, so you have a template processor, you have the configuration templates. The template processor would mount your config map as a volume, takes the templates which are coming directly from the init container's image, processes it, creates the processed images into the configuration file. Your main application just mount and reads the configuration. And of course, the only thing you have to change for different environments is just different config map volumes for different environments. So you would put into the config map only those parts which are different for these environments. Here's how it looks like in the resource descriptor. So you would have here a deployment, and you see the init container just picks up kind of a prepared image which contains the templates. The parameters themselves come from a config map named Wildfly parameters, and the config itself is written into an empty directory, which then later on is mounted by the main container, like here, the Wildfly, and just uses the configured parameters. We have good example for this into so the book has already prepared images which you can directly use for this kind of processing. Next, let's talk about behavioral patterns. Here we are talking about patterns that are describing the characteristics of an application, like a batch job or stateful services, but also how services can find each other via service discovery, or how services can be exposed to the outside. And this is what we are describing now with the service discovery pattern. And this pattern is all about how you discover and use services with Kubernetes in different variations. First of all, let's have a quick look to the non-Kubernetes world and how service discovery works there. So typically you have a producer, so this is the one who offers your service. The producer registers its service in a service registry, like console, for example. And then you have a consumer who needs to do an active lookup to the registry. For example, with a name, it gets back a reference to the service and then invokes the service in the third step. Sometimes there are agents involved which you have to connect to your services. With Kubernetes, it's a little bit different because the service registry is really part of Kubernetes itself. It's all that the consumer already has a name for the lookup, and this lookup happens behind the scenes. So this is done by kind of a proxy. This is either a real proxy or kind of a virtual proxy. And you can imagine this is the Kubernetes service which is used here. And so in that sense, the proxy also selects the pods and invokes the service afterwards. Now let's have a look into the different kind of discovery. So first of all, we have internal service discovery, which is used by services or by application pods which are running within the cluster. So every application has kind of dependencies, and these dependencies can be either within the cluster or outside the cluster. If they are within the cluster, you can just call your dependencies via a Kubernetes service. And this service is kind of a mini load balancer for your pods. And these pods are selected by label selectors. You can have multiple services per pod. There's also you can configure a session affinity on an IP address of the client pod, so that a client pod with a certain IP address always lands at the other fixed pod. And readiness probes are really used to indicate that a service is ready. So if you call a service, you only get through you only get to a pod that is ready, and you get a virtual IP address for each service. So you do an internal lookup via DNS and then get back the internal virtual IP address of that service. If you have to access services outside the cluster, so like an external system, you can do this also with the Kubernetes service. But in this case, you don't enter a label selector into the service, but just either create so-called an endpoints resource, which has a list of IP addresses that should be used. And this endpoint has the same name as a service. So in this case, if a request comes from a pod to this service, then the endpoints are consulted and then just delegated to the external system. Or you use a service of type external name, and there you can just put in an external DNS name, which then is used all the time if you access the service. So this service is then kind of a proxy for this external name. So this was all about how your internal pods can access services, but of course, sometimes you want to expose certain services also to the outside, so that a user outside of the cluster can access your service. And here you have different possibilities. The simplest one to configure is the node port. You just add a type node port to a service, and then every node in your cluster exposes this port to the outside world and directs you to this service. And the service again just delegates to the pods. The benefit is, of course, it's easy to configure. The drawback is that if, of course, you need to know that the port is available for you to expose, so you have to manage certain port ranges for your services which you want to expose on your cluster. This is true for every service in the cluster that you want to expose over the node port. And also this port is not always stable. So sometimes, typically you get a random port. You can also pin this port, of course, but this requires tons of management for you. And also for a user running, for example, accessing your service via a web browser, it's not easy, it's not so nice to have to specify a port there. Then you have the other two possibilities to use a load balancer or an Ingress. For a load balancer, this is kind of a service offered by your Kubernetes provider, or typically also a cloud provider. And this is different from provider to provider. So load balancer is something which is outside of the cluster and managed out of the cluster. They have different characteristics also. But what you do for your service, you define the type load balancer, and then you have a kind of a one-to-one relationship from a load balancer IP to your service there. The alternative is to use an Ingress, which is a kind of an own resource entity, which is managed within the Kubernetes cluster. You have an Ingress controller behind that, and this Ingress controller also exposes the Ingress to the outside. You can also dispatch to multiple services. This is not so easy with a load balancer. Here's the example how you specify an Ingress. As you see, you can specify different context paths, which is nice so that you can really dispatch to different services. So this is all what I have about the service discovery. What you see here is actually a short summary, how you specify this on the service. So there are different types and different other specifications which you can use and which map to these different concepts. So finally, let's have a look into the advanced patterns. And these are patterns which do not fit really well in the other categories, but they are described more advanced concepts like elastic scale, which is about horizontal pods and vertical pod autoscaler based on current resource usage. And also about image builder, which allows you to create container images within a cluster. But for this talk, I've selected the controller and operator, which are very important concepts of Kubernetes itself. Let's start with the controller. The controller pattern is all about how you get from the current state to the target state. I already mentioned that Kubernetes is all about state reconciliation, which means that it's that you declare your state, what you want to do, and it's up to Kubernetes to perform certain actions to get to this state. This works that it periodically observes the actual state and then analyzes the actual state, makes a diff against the target state that you have declared in the cluster, and if there's any difference, then it acts on in that form that it tries to decrease the gap between the actual and the target state, and of course ideally this gap gets zero so that there's no difference anymore. So this is how Kubernetes works itself. There are tons of controllers who are doing exactly this kind of loop all the time. Technically, it works that the controller connects to the API server. The controller is kind of a regular application running in the background, and then observe the API server. This is by observing events which are emitted by the API server when there is a change in the cluster. Depending on these events, it analyzes whether it needs to act or not. If there is some action required, it again contacts the API server, and this API server then works on behalf of this action, talks with the node components, creates maybe new pods, or does anything that the controller wants to do. As mentioned, Kubernetes itself has a tons of controller, but you can leverage this concept as well for your own applications. Here's an example of such a controller. You can write a controller, of course, in any language. Here we are using a shell script just to demonstrate that you can also use shell for that. What you see here is kind of a curl which watches for events, so it curls the API server, and then it reads the event. And for every event, it extracts the event and checks whether the event has been modified. And for example, it watches for certain config maps by name, and if such a config map has been modified, it takes an action. And this action in this example, which is also part of the books example, which you can download, is to restart a pod which has a certain label that points to this config map. So with this simple controller, you can implement a functionality which means to restart your pods as soon as its configuration changes. Coming now to our last pattern, the operator. The operator is all about how you can encapsulate operational knowledge into an executable software. It's a little bit similar to the controller, and in fact it is based on the controller. So here's a definition of what an operator is. So first of all, we have this very nice quote from Jimmy Zielinski, which really, I think, brings it to the point. An operator is a Kubernetes controller, so it's on top of a controller, but it understands two domains. One is the Kubernetes domain itself, like a controller does, but also something else. And this, by combining this knowledge between the between Kubernetes and this custom domain knowledge, it can automate tasks the same way like a human operator would do when it would have to operate the software. There's another definition which we also like quite a bit because it's very simple. Maybe it's too simplistic, it depends, but actually we also see an operator often as a controller plus something, a new concept, which is called a custom resource definition. And a custom resource definition, or CRD in short, is something how you can extend Kubernetes with your own types and your own resource types. So here you see an example of a Kubernetes resource definition, which introduces a new type, which is called config watcher. And as soon as you have applied this custom resource definition to your Kubernetes cluster, you then can use a config watcher resource like in this example. So you can use a config watcher, kind of config watcher, and then you have a specification spec field, which is very specific to your own resource. And this resource encapsulates your domain knowledge. So for this example, which is based on the controller example that we just have seen, it's about an operator running the background, watching this custom resource. As soon as it sees such a custom resource, it knows it has to watch a config map with the name web app config, and then as soon as this config map changes, restart all pods which match this selector here. Okay, so we can have now seen controllers and operators and how do they compare to each other. This is also a kind of a one view on how you can categorize controllers and operators, and this is based on flexibility and complexity of this. So for example, controllers, which is it's simpler concept than operators, they typically operate on standard resources like labels or also on config maps and other stuff. You can configure them with config maps as well. But if you have a higher requirement for your domain, then you probably move on to operators that are watching custom resource definitions. Or if you want it even have it more complex and more flexible, you can create an own aggregate API which hooks directly to the API server, and that so that you can be accessible via the REST API directly from the API server. Then there's another classification which you can put on custom resource definition themselves. So we distinguish between installation CRDs and application CRDs. Installation CRDs are really about how you can operate an application, like Prometheus, like in Kafka cluster, like anything which you want to run in your Kubernetes cluster, and how you want, and this installation CRDs describe the installation of the application itself. It also is responsible for the updates, so the operator behind the CRD is responsible for updates and other operational tasks like backup and restore. A good example is, for example, Prometheus. So there is a CRD which type with kind Prometheus, and this is for installing a Prometheus monitoring system for you and all the dependent components to that. Then there are the application CRDs, and this is really about the application-specific concept, whereas the installation CRD is really about installing something and taking care that it's really constantly running. The application CRD is more about configuring these applications. Yet another example is the service monitor, which is there for registering Kubernetes services with Prometheus, so that as soon as you install a service monitor, then your Prometheus server will monitor the service which is referenced within the service monitor. Other example could be a Kafka topic, which is also available if you use, for example, the Stringy operator, and this would introduce a Kafka topic in your Kafka cluster. If you are looking for operators which are there, the operator hub is a very good starting point. It contains a catalog of available operators. It contains instructions how you can install these operators in your cluster, and this catalog is constantly growing, so I really recommend to go to operatorhub.io. If you want to create your own operators, you have tons of possibilities. There is you can of course write it in any language, but there are some frameworks which can help you to create those. The most famous one is the Operator SDK, which you can find on GitHub, and this allows you to create operators in the Golang language. So this is all what I have for you, thank you very much. I hope you enjoyed the session. You have seen some of the operators. You find more in the book that you can download. Yeah, I hope you enjoy the virtual KubeCon, and hopefully next time we can meet us in person again. Thank you very much.